the system of a previous problem, well, this system here, if the hoop and the semi-cylinder assembly is centered on the top of the stationary cart and the system is released from rest, determine the initial acceleration A of the cart and the angular acceleration alpha of the hoop and semi-cylinder. Friction between the hoop and the cart is sufficient to prevent slipping. Okay, so we're rolling without slipping at this point. Roll without slip. And the system is released from rest. Okay. We need to determine the initial acceleration A of the cart and the angular acceleration alpha of the hoop. Friction between the hoop and the cart is sufficient to prevent slip. Motion takes place in the XY plane. Neglect the mass of the cart wheels and any friction in the wheel bearings. So I just drew a side view here, and to understand what's happening, let's just draw the free body diagram of the semi-cylinder assembly. So we have the normal force acting here, friction force, and the weight. Now the weight is not acting at the geometric center of the hoop. It's acting at the center of mass that is different from the geometric center. The geometric center meaning the center of the geometry. Okay, so if I just look, for example, at the weight is gonna create a moment about this point D. Even if I take the sum of moments about this point, I will call it P here. The weight will create a moment about this point P, which is gonna cause the disc to turn. And because of conservations, and because of the nature of this assembly, if the disc turns, then the cart is gonna move. And we need to find the motion of these two parts after the system is released from rest. So let us start with our 4 steps. I will first want to find the position vectors of the center of masses of each of these objects. Let me draw them again. Oops. Maybe I'll just copy and paste. I do want to make my position vectors general, so I will move this cylinder a little bit, and now it's tilted. Okay, so now I can choose an origin. Maybe I'll choose it here. So that this is body 1, call center of mass 1. This is body 2, center of mass 2. The position vector of to the center of mass of body 1, RC1, we'll call it R1 for short, is just X1 EX. This is my origin. And then just remember that EX and EY are like this based on the axes given here in this figure. Then I can draw the position vector to the disk, the center of mass of the disk, which is this one, which I can divide into kind of a horizontal component, a vertical component, and this vertical component is gonna stay constant. It's always equal to half the width of this and then the radius of the disk, and this vector here, which we're going to define this way. We're going to take a co-rotational basis on the disk, EX, EY, and C, with respect to D, always points along little EX. So in this case, this co-rotational vector is like this. I'm going to zoom in. So, sorry, this distance, let us call it D for now, it points along EX, co-rotational EX. So now my position vector R2 is X2 EX plus some constant along EY plus D EX. And I'll differentiate to find the velocity and acceleration vectors. So V1 is X1 dot V2 is x dot 2 ex, this constant goes away, and then plus d theta dot ey. Remember that for the rotational bases, ex dot is omega cross ex, which is theta dot ey, and ey dot is omega cross ey, which is minus theta dot ex. Okay, so this is V2, and A1 is x double dot 1 ex, A2 is x double dot 2 ex. Here we're gonna have to use the product rule because theta and ey both depend on time. So that's d theta double dot ey minus d theta dot squared ex. Very well, that was our first step. The second step is we're gonna draw the free body diagram. So here we can consider the two systems combined or each system on its own. Let us do all the possibilities. So combined system, combined system, copy, paste is equal to the card and the sphere. Okay, so here I have acting on the card two normal forces, and one left and then one right, and the weights W1, W2 is off to the side depending on where my partition is. Okay, and then let us draw the individual free body diagrams to see if we're missing anything. On the ball I have the weight, okay, weight 2, and normal force N2, and friction force. So then we have the minus normal force here, minus the friction force, and the weight 1, and the normal forces on the cartwheels, and one left and one right. Okay, awesome. So this combined system is equal to the other two systems. Okay, I don't think we missed any forces, but we'll keep thinking. Then we have to find the angular acceleration alpha and the acceleration a. So here they want acceleration quantities, so we're probably looking at the balance laws, not their integral forms. So F equals ma and the sum of moments. Okay then, here how many equations can we write? We can write F equals ma for the car, and so the balance of linear momentum and the balance of angular momentum for the car. We can also write the balance of linear momentum and the balance of angular momentum for the disk on its own, or we can sum them and write these equations for the system. But we also have from kinematics, because the disk is rolling without slipping on the cart, we have kind of the roll without slip conditions. So let us start writing all the equations. I don't think we will gain anything. Well, actually, maybe if we write the balance law, the F equals ma for the combined system rather than this system, we might kind of get rid of the normal force. So let us see. But in the horizontal direction, it's not useful. So this is system 1, this is system 2, and this is system 1 and 2. Okay, so for system 1 and 2, we can do F equals ma to get W2 plus W1 plus N1L plus N2L, N1R, okay, is equal to the mass times acceleration. Well, the mass times acceleration of what? This balance law is the F equals ma of this plus so F equals ma of system 1 plus F equals ma of system 2. So the linear momentum of the system is the sum of the linear momenta of the constituents. M, I think it was big M, A1 plus small m, A2. And just for reference here, we're gonna use the forces. So let's just write their expressions. W2 is minus mgey. W1 is minus m big M gey. N1L and N2L are vertical. N1L ey, N2L ey. N2 is N2 ey, and the friction force is along Ex. This quantity can be negative, so it can be along minus Ex. Okay. So we will get from the acceleration side that it's equal to m x double dot 1 Ex plus small m, and now we have this. A2 is x double dot 2 Ex plus d theta double dot Ey minus d theta dot squared Ex. Okay, and since we're looking initially, since we are considering, we are looking at the initial time, or we are considering the initial time. When the system is released from rest, we have theta dot is equal to 0, and also the co-rotational bases are still going to be equal to the fixed bases, as small Ex and big Ex are the same, and Ey is equal to big Ey. So then in this equation, this term cancels out, and this is equal to big Ey. So if I project along Ex and along Ey, I will get dot Ex, I will get that 0 is equal to m x double dot 1 plus m x double dot 2. So notice here that the linear momentum of the system is conserved along Ex. Linear momentum the linear momentum of the system is conserved along Ex. And if we dot with Ey, we will get that m1, m minus m2, so minus big mg actually, minus small mg plus n1 plus n1r plus n1r is equal to m d theta dot double dot, or that's the alpha we want to find, Ey. Well, Ey goes away. Okay, very well. So now counting our unknowns, we have x double dot 1, x double dot 2, and theta double dot are our unknowns. Oh, and also the normal forces, and L1 and then Lr. So we definitely need more equations. We can write the balance law, the F equals ma, for one of the other two systems. So maybe we'll do that for the disk on its own. We will try. So that's for system 1 and 2. Now for the system of the disk on its own, for 2, we will have F equals MA. So the forces acting on the system are N2 plus FF plus W2 is equal to MA2 N2 EY plus FF EX minus MGEY is equal to M x double dot EX. So I'm just looking here. Plus D theta double dot EY. So then dot EX, we get that the friction force is equal to M x double dot, and that's x double dot 2. So here we added an equation, but we also added an unknown, which is the friction force. And dot EY, we will get that N2 minus mg is equal to m d theta double dot. So added an equation, we did not add unknowns, so we're good. So if I'm counting my equations so far, I have 1. I need a different color. Maybe this. 1, 2, 3, 4. So 4 equations, but I have 6 unknowns. So now I need to do get 2 more equations, the balance of angular momenta. Well, let us see. The balance of angular momentum for this system might not make sense. Maybe we'll do it for this. Let us see. For this, if we sum the moments about the center of mass, so for 2 also, MC is equal to H dot C. Okay, the moments about the center of mass C, the moment of the weight about the center of mass is 0, but N2 and the friction force, they have moments about the weight. So that's RP minus RC crossed with the friction force and the normal force N2 is equal to H dot C, which is IC ZZ theta double dot or alpha easy. Very well. Now I need to figure out what this vector is. RP minus RC. Okay. So now I'm going back to my initial figure. RP, I can write RP as x2EX plus that width over 2 EY. So if I look at RP minus RC or RP minus R2, that's gonna be equal to that C we said is the width over 2 plus R. So minus REY. Okay, I think it's easier to do R2 minus RP. R2 minus RP is REY, that's just a sign flip, plus DEX. So from D to be able, from P to be able to go to C, I go up by REY and then this way by DEX. So R2 minus RP is REY plus DEX. We want the opposite here. Minus REY plus D. Initially, EX and small EX and big EX are the same. So that's that. So gross product becomes minus REY cross DEX plus FF EX plus N2 EY. That's equal to RFF easy minus DN2 easy equal to ICZZ theta double dot easy. Okay, so dot with easy, I will get that RFF minus d n2 is equal to I c z z theta double dot. Wow. Okay, that's the fifth equation. We did not introduce, or we did, n2. N2 is an unknown. Okay. Okay, fifth equation, but now we have 7 unknowns. So I think we're gonna end up needing to do the balance of angular momentum about the cart. Okay, so for 3, we're gonna have to do, for system 1. That was for system 2. Okay, first T1 and 2. Okay, for system 2, the MC is equal to H dot C, and here I have to specify that previously we were doing for system 2. Okay, MC is equal to H dot C for the cart. And remember that we're doing this initially. So initially, the normal force N2 is aligned with the center of mass of the cart, so it has no moment about it. The friction force, it will have a moment. The position vector to the friction force is going to be the width of the cart over 2. Is that what's given? No, so maybe we will not need it. I will see what I'm missing. W width over 2 EY crossed with FF, or the minus of the friction force EX. Plus the moments of these two. But these distances are not given, so maybe we don't end up using them. I will say that's length over 2, length over 2. Minus L over 2 EY. EX. Cross N1 LEY plus L over 2 EX cross N2 LEY. Okay, is equal to, well, 0, because the cart is not rotating. Okay, so that's technically our sixth equation, but we do not know these distances L and W. So I'm thinking we will not end up needing this. Well, what other equation do we have? We have the roll without slip condition. Roll without slip. So V C or V2 minus VP is equal to omega cross R2 minus RP. Okay, and here we have to be careful. VP is not actually 0, it's equal to the velocity of the cart. So V2 is this and VP is this, x dot 2 EX plus T theta dot EY minus VP x dot 1 EX is equal to omega EZ crossed with R2 minus RP, which is REY plus T EX. We found this earlier here. Very well, I'm gonna go on with the cross products. Minus omega R EX plus omega d ey. So I can project. So initially ey is equal to ex. Well, should I say that because I want to take the derivative of this equation? Let me just take the derivative of this equation. I will get that a2 x double dot 2ex plus d theta double dot ey minus d theta dot squared ex minus x double dot 1ex is equal to minus alpha r, or theta double dot r, plus theta double dot d ey minus theta dot squared d ex. Okay, so then these two terms have went away. And we're left with x double dot 2 minus x double dot 1 is equal to theta double dot r. Okay, that's equation number 7. Okay, so then technically if we have L and W, we can solve for 7 equations, 7 unknowns. But we don't have L and W, so we're solving less equations. So just looking again at the equations to try to make a plan. We have this one and this one and this one and this one and this one. Okay, so then these equations 1, 2, 3, 4, and 5, they have the 5 unknowns, which are all of these unknowns except N1L and L2L. So we can solve 1 through 5 for x double dot 1, x double dot 2, theta double dot N2, and the friction force. Wow, that's a long problem. And actually we're not done yet because we still need to find these two quantities, D and IC/ZZ2 from geometry. I will pause this video and I will continue these calculations on another one.